the reaction quotient, which represents the actual concentration of the reagent present, we can therefore apply a correction factor, the RT log Q. And we talked about that, and we talked about that as the reaction proceeds and the Q is approaching equilibrium, that the driving force here, which is delta G is negative, becomes progressively less negative till it equals zero, and then we had delta G, so at equilibrium,
December 2nd, Friday.
at equilibrium, we had 0 is equal to delta G0 plus RT ln Q ln K, and so we ended up with another important equation, delta G0 is equal to minus RT ln K. And from the delta G's of the reaction, standard values, we can calculate the equilibrium comes. You don't have to even go in the lab and measure it. Well, now we're going to use this very, very same relationship up here to take care of the problem we talked about in terms of reduction potentials, concentrations not being at standard values. And the important fact for us to remember is that we have the delta G0 is equal to minus NFE0. And of course, delta G itself would be minus NFE, whatever that cell potential happens to be because of the non-standard concentration. Well, we can make a substitution here, can't we? We would have minus NFE is equal to minus NFE0 plus RT ln of Q. And if we divide through
what those terms are.
by minus NF,
In the book color?
and we get a nice little compact expression that E is equal to E0 minus RT over NF ln of Q. This is a very, very famous equation in science. It's known as the Nernst equation. And what it says in words is the same thing we were saying in words up there on the top, is that we have tables of standard reduction potentials, and so we can calculate the E0 for the cell, just as we were doing up here a few minutes ago. So you go to the tables and you reverse the right half reaction and get the E0 for the cell. And now this term here allows us to compensate for the fact that the concentrations are not standard concentrations.